Hello everyone, and welcome to the talk where we'll tell you about Vulkan optimization on mobile. So my name is Arseny, I work at Roblox, and I'm presenting with Joe from ARM. When Roblox was being ported to Vulkan and optimized for Vulkan, which was a couple of years ago, the amount of resources out there about what is slow and what is fast was basically nil. Like, it was really hard to figure out what to do apart from experimenting. So the good news is that today there is a lot of tutorials, best practice guides, code samples, etc., and some of them come from vendors, and you should trust vendors to know what performance is like with Vulkan. So we'll start with Joe telling you about ARM best practice guides, samples, and tools.
Hi everyone, as you mentioned, my name is Joe Rozek. I'm a developer relations engineer from ARM. Pretty much what I'm here to talk to you about is our Vulkan best practice for mobile developers project that we have going. This is a collection of runnable samples and tutorials that our team's been putting together and that we've recently donated to Khronos and is actually available today. These samples are going to be working as a supplementary to the information Arseny is actually going to present. So please go ahead and download them and take a look. Our team's put in a lot of effort to make sure they're very educational and useful for pretty much anyone can get them. Currently, they are available on GitHub. They are all released alongside a tutorial that's going to walk you through the code, and so that way you're going to have a good understanding of what's happening. And on top with that, we've also released a performance graph with each one of the samples. So that way, as you play with all the individual options, you can see how that's going to be impacting your performance as well. On top of all this, we've also included a solid framework, so that way you can actually make your own samples and release them out with ours. This is a multi-platform project, so hopefully it's going to be really easy for you to download and get set up so you can get started with what you're going to be doing. What we did is we implemented our HWC pipe library, so that way when you're working on your project, you can actually get some performance data from the hardware counters. But for a more detailed analysis, we do recommend that you use low-level tools such as Streamline. In the tutorials, we do actually help you set up some of these tools. I'm going to cover a few of those here in a moment, but first I want to talk a little bit more about the framework that you're going to be running into as you work on these samples. We introduced a high-level API to encapsulate some of the objects to make them easier to handle. We're not trying to reinvent the wheel here, but we wanted to make the code really easy to read in that way so we can very much focus on the parts of the tutorials that you're going to be paying attention to. We also wanted to make something that's going to look a lot like what something a game developer would see on their day-to-day. Well, while we didn't make an engine, we did make a tool that's going to make a tool so you can keep a close relationship with the underlying Vulkan structs, so that way you can keep learning and experimenting with the API. We also wanted to demonstrate some of the tools that the ecosystem has to offer help when you're developing in Vulkan. So we implemented the Spear V cross for shader reflection. This is going to allow you to automatically generate some of the necessary objects based on your shader inputs and outputs. We also brought in a GLTF library, so that way it's going to be really easy for you to import your own modules and scenes, so you can use your own assets while you're developing and not just ours. So this is just going to be a quick overview of some of the objects you're going to need to initialize in Vulkan. In orange, we have the main objects, and then in blue, we have the dependencies that are application defined. For recording commands in a command buffer, we will need the graphics pipeline, maybe a descriptor set, the vertex and index buffers, which in turn are going to be required by these Vulkan objects. In a typical Hello Triangle application, you're going to have to set all these up by yourself, but with our framework, it's going to help you get these set these up in a dependency hierarchy for you, so you're going to be spending more time developing and experimenting than just getting set up to be able to do what you're wanting to. Furthermore, using the shader reflection that we've implemented, you can do a lot of the heavy lifting in the framework and initialize many of these resources based on the shaders. This is going to allow you to focus on writing your shaders and optimizing your pipeline rather than just doing the nitty-gritty stuff. Reflection can parcel shaders and initialize the bindings with the straightforward information such as the type, the size, or the shader state. So we're only going to need to update the actual values when you're drawing. So when we put them together when defining our render passes, the framework provides an enhanced command buffer to help make the recording more readable and stores the references when necessary for the objects for you. For a simple render pass, we shall provide the render target and the frame buffer. Then we bind the resources we initialize, and finally the vertex buffer and indices for the drawing in this example. The framework API then organizes the objects into high-level abstractions. There we go. A render target is just a place for managing the images and some of the common attributes. A render frame manages the render targets, and render context manages the frames. So pretty straightforward. We have also provided helper functions that's going to help you start and end a frame. This is going to handle things such as invalid swap chains. And in this example, we can see how we can define 4 render passes. Each stage provides a render target that we combine the resources, and finally do the composition. So in the samples, you will actually see a high-level view of these events. Most of the code is abstracted in the framework, except where we would like for it to show you particular best practice tips, where we'll override the framework so that way we can very clearly show you what we're wanting you to see, and so you can learn what's the process. Sorry, I'm not good at PowerPoint. But now that we kind of have understanding of the framework that you're going to be working with when you're working with these samples, let's go ahead and look at some of the tools that are going to be really helpful for you when you're developing in Vulkan, particularly with debugging and performance. Earlier, I mentioned Streamline. This is a tool that is actually developed with us at ARM. It's a really high-level view of it. It's going to be a performance analyzer. What it does is it's going to take samples from a software that's running, and through program counter sampling, it's going to give you access to the GPU, the CPU, and OS level application monitoring. All this is going to be visualized in a timeline, so you can see where the system is going to be spending its time, and you can see if there's going to be a bottleneck in the CPU, the GPU, or even the memory. Then, if you detect a bottleneck, you can actually take a little further look into these processes and see which functional units are going to be your critical path. So for example, in shading, it's going to either be your mathematic, your texturing, or again, your memory. There's a few other additional tools out there for you that's going to be really helpful. These are going to act more as debuggers though. The first one I wanted to talk about, and is one of my personal favorites, is going to be RenderDoc. RenderDoc is a really great tool. They've spent a lot of time making sure the usability of the tool is pretty high. So that way you can get it installed and working pretty quick, rather than fighting with your tools to get those installed. The second one is Gapid. Gapid is pretty cool. Once you get a target of an application, you can actually disconnect it from the target, and then inspect all the commands made by the application. With the tool, you can actually replay the command stream, letting you visualize the frame composition step by step through each command and inspecting the driver state. It also supports modification, allowing you to adjust the command parameters and different shaders. So that way you can kind of see how the shader is going to influence each individual frame. And then finally, we have CodeXL. This is a comprehensive tool suite that enables developers to harness the benefits of GPUs and APUs. It includes a powerful combined host GPU debugging and comprehensive GPU profiling as well. It also supports the Boltzmann driver, as many AMD GPUs and APUs as well. So it's a really good tool to use alongside our Streamline, which supports Mali and ARM GPUs. Now that you kind of have a good understanding of like the resources you'll be able to play with when you're implementing Vulkan, let's go ahead and bring Arseny back up so we can talk about porting Roblox to Vulkan.
All right. So before going into this, let's ask the question that people may be asking themselves: what is Roblox? So for people who don't know, it's an online multiplayer game creation platform. Emphasis on platform, meaning we don't really create the content. I will show a couple of screenshots from the games that our users have created. We mostly have nothing to do with them. So we run on a lot of platforms, and of course for this, the most important one is Android, because this is where we use Vulkan. And we have a lot of users, so if you haven't heard of us, it's probably because our primary age demographic doesn't really intersect with you or people who you are familiar with. So here's a few kind of examples of what does Roblox look like. This is a screenshot from one of the top games. I think it has 40, 50K concurrents roughly. It's a GTA-like game. That's a dungeon combat crawler game with cooperative mechanics. That's not a game, I think that's a showcase that somebody built. And that's also a screenshot from some other piece of content. So you can see the content is pretty varied. The content is created by our developers, by our community. Our job is to make the engine, to make the distribution platform, etc., and make it run on all platforms. Why are we even talking about Vulkan? So Android is a very big platform for us, and Android is also a very, very hostile platform performance-wise. Things are slow there, the devices are slow, the software is slow, profiling is really challenging, and we are not in control of content, so we can't just optimize content for the target device. So what do? Well, we said, hey, maybe Vulkan will help us, and started porting to Vulkan. The stance on Vulkan that we have is kind of, it's between investment that helps us right now and a good long-term investment, in the sense that it would be really nice if at some point in the future we will not have to support OpenGL in any of its incarnations. And there's other benefits that come from Vulkan. For example, Vulkan has a lot of good open source SPIR-V-based compiler tools. I think there's a general industry move right now towards adopting SPIR-V as the interchange format for the compiler tooling on the shader side. And we've converted to SPIR-V-based tooling for all of the APIs that we support, not just Vulkan. And in theory, you can use Vulkan on other platforms. I say in theory because we never tried. We actually don't use it on Windows right now, just because on Windows, you have good hardware, you have really good drivers, more or less, and between both of those, like Vulkan is not as interesting, whereas on Android, performance is really, really necessary for us. This was a long and arduous process. I will not go through the details of the long, arduous process. Suffice it to say, it took time. It took time to get something that works. And again, as I mentioned in the beginning, we did this before there was really good documentation, etc. So a lot of this was kind of stumbling in the dark. Let's try this, let's try that. That doesn't work. Oh, I guess it's a driver bug, or maybe it's a bug in our code. Nobody knows. And of course, once we thought, okay, we are done, our code is awesome, it works, it's validation, clean, ship it. And then it took us like half a year or more to actually ship it on Android, because the state of the ecosystem at the time was not amazing in terms of robustness. But things are improving. So as you can see, at this point, we have more than a third of our actual users on Android. The stats are based on our Android user base use Vulkan, and these stats are slowly climbing up. And this is despite the fact that we actually started with supporting Vulkan really aggressively on every single device from Android 7 that could run Vulkan in theory. But on Android 7 specifically, the drivers were so early and so rough that this year we decided that we should stop supporting these. So this is why you see between December 2018 and February 2019, there is a jump down in Vulkan market share for our user base, because we said we just don't want to maintain Vulkan on Android 7.0 anymore. But since then, stats have been climbing, so hopefully at some point next year it will cross the halfway barrier, which would be nice. All of the other devices are using OpenGL, obviously, so we don't have, we can't say we don't support a device. We say we either support a device with Vulkan or we support it with OpenGL. OpenGL, yes. So different people have different porting experience, and you often hear, well, you really have to redesign your entire renderer about Vulkan. For us, we didn't do this. We didn't do this for two reasons. One is we have a lot of graphics APIs. So we still support every single graphics API that's in this list. Yes, we still support D3D9. D3D9 is awesome. We have like a couple of % of users on Windows from D3D9. All of this runs through the common interface. We could redesign this common interface to fit Vulkan best, and then re-implement all of the other APIs on top of this. There's two problems with this. One is Vulkan concepts are not very ergonomic. Joe was just talking about this where there was this list of here's every single thing that you have to create to draw a triangle. This is not a very friendly way to write graphics code, right? And for us, performance is important, but also we have a small team and a lot of features that we want to write and support on various platforms. So we want an abstraction that's really easy to use, which often means it can't be super Vulkan friendly. And the other reason was when we started porting to Vulkan, Vulkan was a very, very small portion of the target market, right? Today, Vulkan and Metal are growing larger, but at the time, it wasn't obvious why we should even do this. And it's still not super obvious, so I think the more correct way to describe it for us is that we are slowly evolving our interface to fit Vulkan slightly closer, but mostly it's been working out fine. So here's how our rendering code looks, more or less. This is like actual code from it's not actual code, it's like actual lines of code from various places put in one slide so that it sort of makes sense. You see it's very, very immediate mode. There's few objects. You say begin pass into a frame buffer, which is a concept we inherited from GL. You specify some extra parameters that I'll talk about later, and then you say here's my shader program, which is a set of shaders. Here's my constant buffer. Here's my data from C side that's just like a struct that I also want to be accessible to the shaders. Or here's my texture with a sampler state. The reason why sampler state is bound to the texture is because in D3D9 and in the OpenGL, these concepts are tightly linked together, so this is what we do still. And then you say I want to draw this geometry, it's a bunch of triangles, here's how many, that's it. And then you say I want to enter pass. So we have explicit pass boundaries, but otherwise there's a lot of this like immediate mode, I want to bind the texture to slot 0, etc. We did a few changes when porting to Metal for this interface. For example, you see begin pass and pass. This didn't exist before we ported to Metal, now it does. But when we ported to Vulkan, this interface mostly survived intact. The actual interesting bits are in implementation, right? So, okay, this is not super naive, but it's like, it's not what people tell you to do, right? We don't pre-create descriptor sets, etc. Obviously, the driver can do better than this with OpenGL, right? Wrong. So for us, all of this is about trade-offs, right? We want to spend a reasonable amount of time achieving the maximum performance. We don't want to spend inordinate amount of time to get the last 0.1%. We are seeing really good performance. We're actually seeing really good performance on Windows as well, where we haven't shipped Vulkan yet, where we are matching D3D driver performance in a very interesting way, where on NVIDIA and AMD, there is the threaded dispatch, and we can record the entire command buffer with Vulkan faster than the D3D driver can offload the command generation work to a separate thread, which is nice. But on OpenGL, on mobile, we are basically seeing 2 to 3 times faster CPU dispatch performance everywhere, like ARM and all other vendors. So I have some numbers from ARM here where this is measuring, this is not like a micro benchmark, this is not a particular stress test, this is measuring our entire render frame with the profile timeline capture. So you see it involves frustum culling at the very beginning, like query frustum under scene, and a bunch of other not really graphics API specific bits. And then there's a whole bunch of actual rendering work that is both the driver work and our own abstraction and our own high-level rendering code. And across all of this, we still on this specific device, we see almost 3 times faster performance. And obviously, since a lot of these bits are now not Vulkan related, we could push further, like the actual differential between Vulkan and OpenGL is higher. And this is all in a single thread. So that's really nice. Now let's talk about a couple of specific examples of what does this, what do these trade-offs look like, right? When we say we want a really easy to use rendering interface and we want to support it with Vulkan, we want to write a Vulkan implementation that is reasonably optimal for mobile hardware, but also reasonably optimal for desktop hardware in case we port to desktop in the future. So let's talk about render passes first, because this is the first complex topic. Render passes involve a lot of things. Render passes involve load store actions. So when you start the render pass, you have to say, hey, do I want to load this memory, do I want to load the contents of this render target from memory into the tile or not? Image layout transitions, a bit less of a concern on mobile, but on desktop, on some architectures, on AMD specifically, there's really expensive transitions that may happen when you say, hey, I rendered into a depth target and now I want to read this depth target into the shader, and if you never want to read the depth target into the shader, you should know, and you should tell the driver so. And also, you have to have appropriate synchronizations, so you have to insert pipeline barriers. How do you manage all of this is not very clear, right? Do we do all of this tracking automatically in the interface implementation, or do we force the user to adopt the Vulkan model where every single time you want to synchronize, you insert a barrier manually? How should this work, right? So there's an ARM tutorial, actually 2 ARM tutorials that talk about some of the performance implications of some of these different choices, which is great to look at offline, but I'll talk a bit about what we do. So here's what we start with. We start with, on mobile, load store actions are the most important thing to get right. Because if you don't get them right, you have a lot of bandwidth waste. And Benjamin talked about this yesterday, actually, on Call of Duty's example. So because of this, we say, okay, the high-level code should specify the load store metadata precisely when you begin the pass. So this is what the, if you see the begin pass, call at the end, or I guess here there are 2 zeros, which is not very interesting. But here there is 0 and mask color 0. The first 0 is the load mask. It says what attachments do we need to load. The second is the store mask. So this says I don't need to load anything because I'm probably drawing a full screen quad or something like this, but I need to store the entire color 0 attachment back to memory. So this was really important for us to get right, and this is also the only thing you need to get right in Metal, which is why we specify it explicitly. Turns out everything else, basically, you can infer from these 2 bits with like 80–90% accuracy, not being fully precise, but being precise enough that it works for us. So yeah, when you begin the pass, you basically have to specify this explicitly, and also you have to specify the clear metadata. Like I want to clear color 0 and depth with the clear values. We don't even have support for explicit clears, I think, because explicit clears are a bad idea on tilers anyhow. And here there's also the pass resolve, which we'll get to later. And all of the APIs immediate mode, and then our backend just caches the actual Vulkan render pass and frame buffer instances. We have so few of those, and the creation of them is fast enough, then it's not really a big issue in practice that we don't pre-create all of them up front. It's okay. So load store actions, I guess I covered this briefly. The nice thing is that if you explicitly specify every single piece of metadata around load store actions, you can use this in other APIs, so we use this in Metal. We also use this in OpenGL when the driver gives us the sufficient amount of functionality around this, I guess. And there's many cases where a naively written desktop renderer would just say, I want to load everything and store everything, but you don't need to, right? If you clear, you don't need to load. You should just tell the tiler that you should clear. You almost never need to store depth, except if you need depth for post-processing effects. When you do post-processing, this was kind of an example earlier, you don't even need to load or clear. You can just say, I don't care what the contents of the tile will be. And in our case, if you say, I don't need to load, and if you say, I don't need to clear, we automatically say, well, I guess you don't really care what the contents will be. So it's all inferred from these 2 masks, the load mask and the store mask. All right, so how do we infer everything else from this? So the first thing that we need to figure out is image layout transitions, right? So the image can be in the color attachment state, which says you can render to it, you can blend into it, but you can't really read it in the shader. Can be in the shader read state, which says you can't render to it. You have to manage all of these transitions yourself. On mobile, a lot of these transitions, I think across all vendors, are no-ops. Some are somewhat expensive, but most are no-ops. But it's still nice to get this right. It helps desktop in some cases. So we adopt the concept of what's commonly known in DX12 ports as the default resource state, which is frowned upon in DX12 for somewhat good reasons. But for us, with our render structure, it works really well. So the way this works is we say, okay, when you create a shader, when you create a texture, you can create a texture as a render target. And you can specify, do you want to ever read it in the shader or not? And then when you say, I want to start rendering to this texture, if we need the contents of this texture in the current pass, so if you, for example, begin the pass and say, I want to continue rendering to this texture, which you should not really do, but just in case you do so, we say, okay, cool, we think we know what state this texture was in before, because if it's, for example, if it's readable in the shader, we probably have transitioned it to the shader readable state. There's one crucial, this seems very suboptimal, because if you take a texture that's readable in the that's readable from the shader and then you begin rendering to this texture, you have to transition from shader readable state to color attachment optimal, and this causes some suboptimal effects. So this seems problematic. For us, this works for two reasons. One is we aggressively use undefined as the source transition, which some vendors told us might be a bad idea recently, but we'll work through that. But generally speaking, it works fine. So what this means is if you don't care what the contents of the texture was, then really you don't care what state it was before. So you don't have to know whether you were rendering to this texture before, or whether you were reading this from a shader, or maybe this was a present target on the previous frame. It doesn't really matter, because you don't really care about the contents, so you can transition from undefined to color attachment. And if you don't store the texture, you can keep it in its current layout. So if you don't store the texture, because storing assumes either you'll need it in the shader, or maybe you'll render into the texture again. But on mobile, you shouldn't really do this anyway. You should try to render the entire texture in one pass as much as possible. So these things happen very rarely. So these kind of bits of metadata that are reasonably easy to understand help us solve this time travel problem, where we don't really know what the texture will be used as in the future, and we could know what the texture was used as in the past, but this creates complications with multi-threading. But with this setup, it allows us to have this partial information that says, well, you aren't storing into the texture. I guess you won't need the contents that you have just rendered to it. Or you don't load from the texture. I guess it doesn't really matter what you were doing with this texture in the past. And for us, most of the texture fit into this pattern. And synchronization at this point is relatively straightforward. It's very, very similar. If you have to store to the texture, you assume that it's going to be readable in the shader. Really, really crucial that it will be readable in the fragment shader. And this is our default setup, right? Like our default assumption is if you're rendering the texture from a render pass, you're gonna read it in the fragment shader, and then we insert the appropriate barrier for this. If you don't specify the fragment shader bit, things will be suboptimal on Tyler specifically, because potentially the entire binning phase in the next pass will be blocked by your fragment shader workload. The good news is we don't really have any cases where we need, like if you have cases where you render the texture and you want to use it in the vertex shader, in our case you'd have to annotate this with extra metadata. It says, okay, I'm gonna need to read it in the shader, but it's not just any shader, it's a vertex shader, which is more expensive. But for us, in our actual frame, this doesn't really happen, so it's fine. Speaking of other things you can do in a Tyler, so in Vulkan there's two concepts. There's render passes and there's subpasses. And again, if you look at documentation around really mobile-friendly renderers, there's all these beautiful examples about how you structure your entire renderer as a set of subpasses, and you put them on an giant render pass, and it works and it's beautiful, and we don't do any of that. The thing we do is we do an optimal MSA resolve. MSA on mobile is good, it's fast, it usually runs, like if you set it up right, you render with MSA in a tile, and then the tiler resolves from this tile directly into memory. So it's really, really low cost. You don't get extra shading cost mostly, you don't get extra bandwidth cost mostly, you don't even have to spend memory on MSA targets. which I'll talk about in a second. So this is the only thing that we do in terms of subpasses, and it works really well. The way this works is when you begin the render pass, in our render you're supposed to tell it exactly there, we will need the resolved version of this target, and please put the resolved version like in that texture. And then we synthesize the correct render pass definition and structure and all of this. The optimal setup is you should clear your MSA buffer before rendering into it, but you should not store it at all anywhere. That's really expensive. And then your actual resolved texture, you don't really care what context was before rendering, but you should store the resolved data in that. And VKCMD resolve image is a way to do MSA resolve without render passes. On mobile, on tilers, it's really expensive. We do support the slow resolve path. We use it on desktop where the render pipeline is more complex. So you do need to resolve the same buffer like several times because you need the contents of your color, texture, for some transparent objects if you want to implement refraction or something like this. But we try to avoid this. And we don't use this on mobile. We don't use CMD resolve image on mobile at all. And yeah, like if you have an MSA buffer, you still need to allocate the entire buffer. That's a lot of memory. If you're talking about like a 720p device, that's like 28 megabytes of memory for 4x MSA, which gives you pretty good quality on mobile. Which, you know, by desktop standards, this is nothing. By mobile standards, it's not nothing, especially if you have lower-end devices. So with Vulkan, what you can do is you can set up your image as a lazily allocated image and specify the correct bits in the frame buffer. I think ARM example about render passes talks about this, so I won't go into too much details. Again, there's surprisingly little annotation that you have to do to get this going from the high-level rendering perspective. Metal supports the same feature, which in Metal is called memoryless targets. For us, what it boils down to is when you create a texture, you can say it should be the render memoryless texture, which means you can render to the texture, but you can't render to the texture twice, for example, while preserving the previous rendering contents, because there is literally no memory allocated for this texture. This is a Metal requirement. Vulkan requirement is slightly more lax, because in Vulkan you can say lazily allocated, but then I think in some cases the driver can allocate memory for this texture. In Metal, I think the driver never allocates memory. And with just this bit, all of the rest of this heavy lifting can be hidden inside the implementation, specifically for Vulkan, right, which is pretty simple. So that's render passes. Right, as a result of all of this, right, we don't currently have a render graph. We probably won't really do a render graph in the next few years. We have an immediate mode rendering, but with a bit of annotations, it seems possible to do more or less, like to do a reasonably good job at doing the right layout transitions and synchronization, especially if your render is already mobile friendly, which it has to be for us. So now let's talk about descriptor set management. This is the other area where we deviate from, in this area we deviate from all the norms. We do things completely differently because the render passes, the idea there is our interface is very close to Metal, and our implementation for Vulkan tries to be really optimal within that interface. For the descriptor set management, our interface is kind of unique in a small way. ARM has a tutorial that covers some of this, but not all of this. So yeah, we commit the syn of graphics APIs, apparently, which is we use slot-based bindings. So you say, I want to bind a texture, and you specify the slot for this texture that you want to bind it to. And as I mentioned, when you bind a texture for shader reads, you specify the sampler state directly, because OpenGL D3D9 are horrible. When you bind buffers, whether it's a constant buffer or structured buffer, like shader store buffer, you just specify the slot. And there's also this bind buffer data call, which you don't even have a buffer object. You just have a struct that you want the shader to be able to read. This is loosely inspired by Metal. There's one crucial difference. You don't specify the stage that you bind the resource to. You just say, I just want to bind the buffer. And if the buffer is buffer1, then it's buffer1 and fragment shader and vertex shader, and we don't actually use any other shaders like tessellation or gram shaders. But it doesn't really matter. Like from the high-level code perspective, you just bind the texture, which on other APIs, it requires a bit of an extra management in the implementation. Because in all other APIs, I guess except for TX12, which is slightly different, you have to say, like in Metal, you have to say, I want to bind to this stage or to that stage. So the reason why we don't do this is because it simplifies the high-level code substantially, but in Vulkan, we found that this helps us tremendously, because the big issue that a lot of renderers hit when porting to Vulkan is that on Vulkan, you can have at most 4 descriptor sets. And then you start to say, okay, so I have the D3D11 binding model because that's what my renderer uses. I have vertex stage, fragment stage, and then like geometry shader, tessellation, et cetera, so like 5 or probably 5 rasterization stages. Okay, each one of them needs a namespace for buffers, needs a namespace for textures, maybe needs a namespace for constant buffers because constant buffers are separate from non-constant buffers in D3D binding space. And now I'll just map each namespace into a descriptor set, and now I need like 12 or something like this in the worst case for my pipeline, but Vulkan's limitation is 4. The good news is we don't really care about things like that. So we have buffers and textures, that's 2 namespaces, that's across your entire shader setup, right, your entire program. So when we build the shader program, which for us is just a set of shader objects, right, shader microcodes, blobs, we, through reflection, discover the specific bindings that it needs. And so through reflection, we can say, okay, the buffer with slot 1 is used in vertex shader, but is not used in fragment shader. So then we'll specify the descriptor set layout that specifies this exact information to the driver. And then the driver can take it from there and do whatever the driver does. Worth noting is that on some mobile drivers, the hardware doesn't even support descriptor sets. There is like 1 that's supported in hardware, so the driver has to merge all of this at every draw call anyway. So for us, it seems like it simplifies the amount of work we have to do and the amount of work the driver has to do, which is nice. Of course, you have to know all of the resources that you need for the draw to update the descriptor set, right? Because of this, all of these bind calls, they basically don't do anything useful. They just record the binding for later, and then at draw phase, we flush the newly bound resource and allocate descriptor sets, update descriptor sets, etc. Allocation, we don't do anything smart there, really. I think basically we do what almost everybody does, which is there's just a bunch of pools of descriptor sets. When you render, you are working, because of the threading requirements, it's like slightly interesting because let's say you are rendering from 2 different threads, and then each of these threads should have a separate descriptor pool. So because of this, we have this pool of descriptor pools where you can say, okay, hey, I want to allocate some descriptors, give me a descriptor pool, and then there's a pool of them so that we don't create and destroy them redundantly, and then we grab one which requires some mutex around some internal bits of the synchronization state, but then you can allocate out of this pool up until you have space in this pool. However, when you create a pool, you have to specify how many sets you need from this pool and also how many resources of each type can live in this pool. So for example, I want a pool with 1,000 texture or with 1,000 descriptor sets, and also this pool can contain 3,000 texture descriptor sets and 1,000 buffer descriptor sets or something like this. How do you set these numbers? So there's 2 approaches that we tried and discarded both of them and decided to do something else. So one common approach is a pool per pipeline object, right? So okay, when you have a pipeline object, you know the exact requirements of this pipeline state, so you can just create the optimal pool with an optimal configuration. Like, okay, this pipeline doesn't even use buffer descriptors, so I'm not going to create any in this pool. So that's nice. The problem with this approach is you have a lot of the single-use or very rarely used pipelines where I have a pipeline for my post-processing shader, and it has exactly one draw call in the frame, almost always. Should I still allocate a pool for this that has 1,000 kind of descriptor sets with, if this post-processing shader uses 7 texture slots, should you have 7,000 descriptors in that pool? It gets pretty expensive for these like rarely used descriptors. You can annotate rarely used pipelines. You can annotate the rarely used versus frequently used pipelines, but it gets complex. The other approach is to just create one type of pool and just assume some worst case, right? So for us, due to some mobile restrictions, we have like up to 16 textures, up to 8 buffers. So okay, cool, we can create all of the sets like this. This is actually what we use for more than half a year in production, I guess. Like every single pool that we would use would have 1,000 sets, and then 16,000 textures, 8,000 buffers, etc. Really simple to manage. The problem is it's wasteful. When we started looking closely at memory optimizations, we said, well, there's a surprising amount of memory that seems to be used by the descriptor pools. Why is that? Well, this is because we don't actually have many draw calls that use 16 textures and 8 buffers. This is a very complex configuration for us. So what we ended up doing for now is that offline, at some point, we looked at a bunch of different things that we need to render, and then we computed this average use case, right? Where actually, in reality, for us, there is 2 average use cases. There is like the depth pass and everything else. But if you only have one average use case, but then you can say, well, in general, most of the shaders that we need, they need like 4 or 5 texture bindings, because you have your like PBR material setup plus like a couple of global textures, and you have a couple of buffers because you need some per instance data and you need some global data. So roughly speaking, the average, the ratios between the number of sets, the number of descriptors, texture descriptors in the set, and number of buffer descriptors in the set is 1 to 5 to 2. Cool. That's how we'll allocate all descriptor pools. And then we carefully manage, you can still allocate a descriptor with disproportionate amount of textures out of a pool while pool has space. So if you have one draw call that needs like 16 textures, it's fine, you can allocate it. The problem is if all of your draw calls need 16 textures, then you have misbalanced your configuration. But this is what we ended up doing. This is like non-trivial memory savings, like tens of megabytes on mobile, on some mobile vendors. And this is also really nice in multi-threading context, because I was talking about how you need a pool of pools, and then the commands buffer that you're recording right now needs the current descriptor set. With this scheme, you only need to keep one current descriptor set. And then if you're out of this descriptor pool, sorry. And then if you're out of this descriptor pool, you just grab a new one. So that's nice, easy, works pretty well. The bindings is pretty straightforward. We mostly just do the obvious thing. We just rebind the descriptor set when we need to. We tried using descriptor set copying, like when you say VK update descriptor sets, you can say what descriptors to copy data from. This seems really tempting. If only one texture changes between 2 subsequent draw calls, should you just copy from the previous one? We found this to be, generally speaking, either same performance on most vendors or really terrible performance on one desktop vendor. So we ended up just not doing this. We always write the descriptor sets from scratch. Our descriptor sets are reasonably small. They're like in the tens of descriptor range. We use descriptor templates from Vulkan 1.1 if available, rarely available on mobile, often available on desktop. On NVIDIA's driver in particular, this is a good reduction in the CPU cost. It ends up matching our internal implementation really well. It's kind of optional, like you can do this, you can not do this, it's fine. So in the Call of Duty presentation yesterday, we talked about caching descriptor sets across non-consecutive draw calls. Like if you have one draw call somewhere in the frame, one draw call somewhere else in the frame, they could use the same descriptor set at some extra CPU cost of managing this cache. We don't do this right now because for us the cost of updating the descriptor sets is surprisingly not that big, but we do cache across consecutive descriptor draw calls. So if you have five like objects with different constants, we don't have to allocate a new descriptor set if they render sequentially. One really important thing, though, is to use the dynamic offsets. So we don't actually have to call bind every draw call, and we don't. The reason is most of our constant data actually doesn't come out of these pre-constructed buffers that are reused across many frames. It comes out of dynamic constant storage. So there's just a ring pool of uniform buffers, and then you need 500 bytes of constants. You just say, okay, cool, I will allocate 500 bytes of constants out of this buffer, and it's probably the same buffer that I used in the previous draw call, it's just a different offset. So Vulkan provides this really fantastic sort of API, where you see the last two parameters of the APK CMT bind descriptor sets are the dynamic offsets, which specify the offsets in the buffer that the GPU should read from. So we use this extensively. This is like the biggest thing that we did that cut the bind count very substantially. So with that, though, there is this trade-off that actually is exposed to the high-level rendering code. So you have these two ways to bind constant data to the shader. One is you create a constant buffer object, fill it whenever, and then bind it. The other one is you can just say, here's some data, just do something with it, right? The first case is suboptimal from the bind perspective, because every time you have a new draw call with a different buffer, you have to rebind this buffer. You can't use the offsets. The second call is optimal from this perspective, but it's suboptimal because you have to copy this data into this shared like ring buffer every time you call this, right? Which generally speaking actually results in a pretty obvious trade-off. If you have a lot of data and it's used many times in different draw calls in a frame, you probably shouldn't copy this data many times, so you probably should just upload it once and then use the bind buffer. Otherwise, if you have little bits of data, just use bind buffer data. And actually all of these things are compatible with arbitrary shader setups for us. So we have some systems where they actually look at the size of data and they say, well, you are instancing objects, and we try to dynamically find a set of objects in the frame that have the same shader setup, etc., but different constants. But turns out we only found 2 of those. So we'll use bind buffer data because it's easier to just copy. Or we actually found a lot of those, so we will pre-create and cache the buffer object with that data. And just some kind of general things that we hit upon. The Vulkan driver is much faster than GL driver. On mobile, it's not always ideal. Like, we are not always happy with the driver performance on mobile, but it's like way better than any GL driver. This means that if you are doing stupid things in your rendering code, they become more obvious, which is great because they become visible in the profiler and you have to optimize them. Specifically, for example, cache misses suddenly become important. Cache misses never really mattered because there is this giant OpenGL driver that eats all the performance that you have. So if you have like a few extra indirections in your rendering abstraction, it doesn't really matter. With Vulkan, suddenly, okay, we can reduce indirection here, like pack these allocations here, and it actually results in measurable performance cost, which is great. For example, we pack all of our geometry setup, all of the buffer objects into one single high-level object. And so when you need to, this is the geometry that was on some earlier slide when you had a draw call, the first parameter was a geometry object, which is like a pointer to this pre-constructed set of bits. And so this means that we can optimally call the right Vulkan calls without touching too much memory that we own. Obviously, if you have a VK function that you don't need to call, don't call it. Like state filtering is still valuable if you are not changing the shaders. It's still valuable to check if you need to rebind things. I talked a bit about contention. One key thing about contention, one key optimization that we are using is this lock-free read locked write cache. Lock-free read locked write cache. What this means is when you only read, it's lock-free, but when you write, we use a mutex, which for things like pipeline objects or some other bits of state is really useful because you tend to fill it quickly, and then you stop writing into this cache for a while, and then you could just read from it directly. You don't need to actually call VK functions. On Android, you can't really bind statically to the Vulkan loader anyway, because there's many devices that don't come with the Vulkan loader, and so you can't run on the Vulkan loader unless you use dynamic dispatch. And so if you are using dynamic dispatch, you can call VK get device proc address, which gets you a function pointer that usually bypasses the loader, which is slightly faster. It's like a few % faster for us on some workloads and some drivers. And in general, basically with Vulkan, it forces you to be a bit more mindful about the small stupid things that you're doing in your rendering code. To finish this off, getting good performance out of Vulkan is actually really easy. I mean, there's a star there because it took us a while, and there were a lot of kind of pain points along the way, but with good documentation that today you have even more of, good samples, and kind of general better ecosystem and better guidance. It's not as daunting as it used to be a couple of years ago. You don't have to, like, if you want to rewrite your renderer, be my guest. You don't actually have to rewrite your renderer to get really, really good gains out of Vulkan. For us, it's like really important to minimize the work that we do on these large-scale refactors, because we have 5 graphics APIs. One of them is OpenGL, which is actually 4 graphics APIs by itself, because there is ES, non-ES 2 and 3, with minor or major differences. A lot of what we did either improves performance on multiple vendors, or improves performance for one vendor without penalizing performance on other vendors, which is really good. There are occasional bits where, okay, it's actually a really good idea to do this on this vendor, but it's a bad idea to do this on this vendor, so it's hard to pick. But a lot of performance work is actually shared, which is great. And of course, use the profilers. And vendor performance guides are pretty great. If you are a graphics vendor and you don't have a graphics performance guidelines for Vulkan, please publish them. If you are like ARM who has them, publish more of them. And that's all I have. That's all we have. And now, if you have any questions to me or Joe, we will be happy to answer them.